Do you think you're ready for this? We're going to take a Hamiltonian for the molecule hydrogen with all its interactions and so on that we've covered. We're going to reduce it to a form that we can capture with one computer qubit. Sounds impossible, and that's why this one is especially fun. Now I added something to this page. Here's the D1, and this is a determinant, one of these 6 determinants that look kind of like this that could go in there. And this one could be another one of 6 determinants that go in there. And the Hamiltonian part in there, and that's why I wrote this down because I had to figure out a way to say it that even made sense to me. How strongly does the Hamiltonian connect the determinant configuration? So this shows how those 2 determinants can be affected by the different molecular properties. That's all of this stuff, the H and the G and all that different stuff we went over in the last video. So let's go to another page and see what's going on. But what I want to emphasize is if we have 6 possibilities here, 6 possibilities here, then that's going to give us 36 possible arrangements of this. And let's see if this next page has exactly that. Oh my gosh. Oh my gosh. Oh my gosh. If you look up here, each one of these is a combination. Here we've got the ground state and the ground state. And I notice that I've got an E here by each of the ground state combinations. Just kind of standing for energy. So this doesn't do a whole lot, the energy parts of the diagonal of this matrix. Now, the different determinants are in this order because they're in increasing energy, where if we're to the anti-bonding stage, the most energy has to be added to get to that anti-bonding stage. And all these are intermediate states that get there. Here's where it gets a little complicated. I've got a bunch of zeros here. And let's see if we can walk through some of the zeros and give you the idea. I walked through every single one of these and found out what I needed to know. But these zeros occur if we change the spin pattern between these two. In other words, if we have a spin up, spin down, and it changes to a spin up, which is exactly what that one does, that violates the exclusion principle. I believe it's the exclusion principle. But anyway, the zeros are wherever the spin pattern didn't change. So let's see how many that takes out. If you look down here, I've got it set up a little bit easier to look at. And instead of all this garbage that we have to look at, here are the diagonals. EGG, EGU with both of them spin up, EGU with spin up and spin down, EGU spin down, spin up, EGU spin down, and EUU. Those are all the different combinations of those 2 different values with spin involved. Now, what is this A and this minus A? Well, that A and that minus A has to do with, well, let's just look at one of them. Let's look at what happens here with this A. That is going to be a single excitation. If you notice, we go from, take this one and bring it up to that one, then that's just one electron that gets moved. So all of the green ones, well, not all of the green ones, the A's and the D's are single excitation, whereas the B's and the C's are double electron excitation. Well, let's see. Is this getting worse or better? Well, at least we got these zeros here. So the zeros is going to simplify it so we don't have to consider any of those things when we go to capture it with a qubit. And this actually takes out half of them. That we go from that many zeros, and then it all crunches down to a, what is that? A 4x4 matrix. So all we have to do is try and figure out what these things are. Now, why is this minus A? I know that's a single electron excitation, but why is it a minus A? Well, let's go up here and check this out. Well, the 1 is moved from the first spot and transferred over to the third spot. And we crossed a 1 there. Now, when we cross that 1, that changes the sign. And we could go in and try to justify all that, but we want to get quickly to the qubit. So let's keep going. But anyway, and if you notice, where's another A minus A? Here's another A minus A. And there's a certain pattern here that these really just are the inverse of what we had up there. In other words, the 1100 is on the right-hand side. Notice that? So the same rules are going to apply. Now let's look at the D. The D goes from a 0011 to a 101. Now let's see if there's anything different there. That is a spin up, spin down, and it changes to a spin up and spin down. So the pattern is still the same. Now up here, is that the pattern? Well, let's see. We've got a spin up and down, and then that goes from a spin up and down. Okay, so there's no changes in the spin pattern. Now let's see what goes on. The same kind of rule is used to come up with the minus sign. If we cross a 1, if the 1 moves and it crosses a 1, then that's going to give us the minus sign. This different color is given to this 0 and this 0. So there must be a reason for that. Well, these are double excitation states. And those double excitation states, they're in at least that diagonal. And those also violate the spin rule, where the spins have to stay the same. So those come out. Now, what's up here in the corners? I've got a B here that represents those. So what can we say about the B? Well, that's just a double excitation for the B. And let's see what happens down here. Well, it's kind of in the reverse direction, but that's a double excitation from GG to UU. Now, if we look at the C values that are on either side of this diagonal line, then what is the C? Well, that goes from a 110. These are exchanges. These are exchanges. So the 1s and 0s exchange with one another. Well, you could say the same thing is true here, but those are called exchanges. And I'm not going to belabor all this. I just want to show that we can keep reducing this down. If we take the A and the minus A, then we get a 1 over square root of 2 equals square root of 2a. A minus minus a gives you that. Now if we take an a plus minus a, that just comes up with a 0. So what's nice is we can combine those two different a states into square root of 2a, square root of 2d. And what is this? EGU minus C. Well, you've got to go all the way up the page, and here's those 4 elements that we crunch down to EGU minus C, and the same thing occurs. We've got an EGU minus C. It is a lower energy, so this EGU plus C is not going to occur because nature wants to go to a lower energy state. So we can just crunch this whole thing down into one value, one element, EGU minus C. So now we're down to a 3 by 3. All right, is that it? It looks like that's going to be pretty hard for one qubit to cover all those states. There's 9 different states there. So let's think about this a little bit. How much effect does the A and the D and the C have on the ground state? Well, I'll show you in another diagram that it has no connection to the ground state. Now, when we go to higher energy orbitals, then these things start coming into play. So they're not thrown away, they're just not needed for the ground state hydrogen molecule. So let's go on to the next one, see if that looks any better or worse than this thing. Well, it's certainly a lot simpler picture. It's taking a while to come into play here. But here we go from this one to this one. And notice I made a 0 out of each of those A's and D's because they have very small effect except in higher energy orbitals. So this all comes down to this form where the EGU minus C disappears. This is all collapsed into a single qubit that has 2 states, EGG for 1, EUU for 0, superposition states that cover all the other conditions that can occur between those. So for ground state hydrogen molecule, that's all we need for a single qubit. And our next challenge is to take this qubit idea and translate it into a computer program on the Qiskit, which is the IBM software set, to actually perform some calculations and see if this really works. Now, to give you an idea, here's another way to visualize this thing. There are 3 decoupled matrices. Each one of them is a 2 by 2. Here's the A and D here in the middle. Here's the C out here. I hope that's enough. Took me forever to put these pictures together, but I hope that's enough so we can go on to quantum computing.